Model input and output chain components. Imagine you have a language model, like a super smart computer that understands and generates human language. This model works by taking in text, input, and creating new text, output. But it can't just handle plain text directly. It needs to be broken down into bits that it can understand. Here's how the model works. 1. Input tokenizer. This is like the first step. It takes your raw text and breaks it down into individual pieces called tokens. Think of tokens like words, but they can also be punctuation marks or even parts of words. For example, the sentence, "The quick brown fox jumps over the lazy dog," would be split into tokens like, "The quick brown fox jumps over the lazy dog." Though, embedding layer, now the model needs to understand the meaning of each token. The embedding layer takes these tokens and converts them into mathematical representations called vectors. These vectors capture the meaning of the word, and similar words get similar vectors. For example, the word quick and fast would have similar vectors because they mean almost the same thing. Decoder layer. This is the heart of the model. It uses the information from the embedding layer to create new text. The decoder layer is like a pattern finder. It looks at the context of the input tokens, what came before them, and then predicts what the next token should be. It's like playing a guessing game, but the model has been trained on lots of text data to be very good at it. Output tokenizer. After the decoder layer predicts the tokens, it's time to put them back together into a sentence. The output tokenizer takes the predicted tokens and turns them back into human-readable text. Post-processing. Finally, the model might do some extra cleaning up. This could be things like adding punctuation, fixing capitalization, or even catching and fixing minor grammatical errors. Think of it like this. Imagine you are translating a story from one language to another. Input tokenizer. You start by breaking the story down into words and phrases. Embedding layer. You then look up the meaning of each word in a dictionary and find its equivalent in the other language. Decoder layer. You use the dictionary and the context of the words to translate the whole story sentence by sentence. Output tokenizer. You put all the translated words and phrases back together into a complete story. Post-processing. You check for any mistakes in your translation and make any necessary corrections. That's how a language model works. It's a complex process, but the individual steps are quite simple, and by working together they can understand and generate human language.
Input tokenizer. Imagine you have a big book of words, but the computer can't read it directly. It only understands numbers. The input tokenizer is like a translator that takes your sentences and breaks them down into little pieces called tokens. Each token represents a word, punctuation mark, or even a special symbol. Think of it like this. Sentence, "The quick brown fox jumps over the lazy dog." Tokens, "The quick brown fox jumps over the lazy dog." The input tokenizer does this by 1. Breaking the sentence into words. This is often done by using spaces as separators. Though, looking up each word in a dictionary. This dictionary is like a codebook that tells the tokenizer what number to assign to each word. Replacing each word with its corresponding number. This creates a sequence of numbers that the computer can understand. Why is this important? Computers don't understand words, they only understand numbers, so we need a way to convert text into numbers. Tokens are like building blocks. They make it easier for the computer to process and learn patterns in language. Example, imagine you have the sentence, "The cat sat on the mat." The input tokenizer might turn this into the following sequence of numbers: the 12, cat, 5, sat, 21, on, 18, the 12, math, 15. Now, the computer can work with this sequence of numbers to understand and analyze the sentence.
Purpose. The purpose of each component. Imagine you have a robot that understands only numbers, but you want to talk to it in English. We need some tools to translate between these two languages. Input tokenizer, the translator. Purpose. This component takes your English sentence and breaks it down into individual words, like a translator separating a sentence into its individual words. Example, if you say, "The quick brown fox jumps over the lazy dog," the tokenizer breaks it down into, "The quick brown fox jumps over the lazy dog. Embedding layer, the word dictionary purpose. This component gives each word a special number code that represents its meaning. Think of it as a giant dictionary where each word has a unique number assigned to it. Example, quick and fast might have similar codes because they have similar meanings. Dog and car would have very different codes. Decoder layer, the storyteller purpose. This component looks at the number codes of the words and tries to figure out the story they tell. It learns to predict what the next word should be based on the previous ones. Example, if the decoder sees the codes for the, quick, and brown, it might predict that the next word will be fox, because that's a common way to finish that phrase. Output tokenizer, the reverse translator purpose. This component takes the number codes the decoder generated and converts them back into English words. Think of it like a translator translating a sentence back into English. Example, if the decoder gives you the codes for fox jumps over the output tokenizer would convert them back into the phrase fox jumps over the. Post-processing, the editor. Purpose, this component makes sure the final output text is grammatically correct and reads well. Think of it as an editor who checks for punctuation, capitalization, and spelling mistakes. Example, if the output was fox jumps over the lazy dog, the post-processor might capitalize the F in fox and add a period at the end.
Embedding layer. Imagine you have a big box of toys, but they're all just jumbled up. It's hard to find what you're looking for. The embedding layer is like a special organizer for words. It takes each word, like cat, dog, or run, and puts it into a little box, but not just any box. This box is in a special word space, where words that are similar to each other are close together. So, cat and dog might be close together because they're both animals. Run might be a little further away, but still in the same area as words like walk or jump, because they're all about movement. Think of it like a map. Each word has its own location on the map, and words that have similar meanings are close together. This word map is really helpful for the model because it allows the model to understand the relationships between words and use that understanding to do things like predict the next word in a sentence. If the model sees the word cat and then it can use the embedding layer to figure out that words like chasing, sleeping, or eating are likely to come next. Translate languages. The embedding layer helps the model understand that cat in English is similar to gato in Spanish, even though they sound and look completely different. Answer questions. The model can use the embedding layer to figure out which words in a paragraph are related to the question being asked, even if the question uses different words than the paragraph. Overall, the embedding layer is a crucial part of language models because it helps them understand the meaning of words and how they relate to each other. This understanding is what allows language models to do so many amazing things.
Purpose. Let's talk about the purpose of each component in this language model system. Imagine you are teaching a computer to understand and speak like a human. Input tokenizer. This part is like a translator. It takes our regular language, like the sentence, the quick brown fox jumps over the lazy dog, and breaks it down into small pieces, called tokens. The model can then understand these individual pieces. Think of it like separating words in a sentence. Embedding layer. This is where things get interesting. Imagine you have a dictionary, but instead of just words, it has a code for each word that tells you how similar it is to other words. The embedding layer turns the tokens from the input tokenizer into these codes. So, quick and fast might get similar codes because they mean almost the same thing. Decoder layer. This part is like the model's brain. It looks at the codes from the embedding layer and uses its knowledge to figure out what the input means and what it should say next. Imagine you have a picture of a dog, and you try to guess what the next word in a sentence about it could be. The decoder layer tries to do something similar based on the codes it receives. Output tokenizer. This is the opposite of the input tokenizer. It takes the codes that the decoder layer produces and puts them back together into a sentence that we can understand. It's like translating back from the codes to regular English. Post-processing. Imagine you're writing a story, and you want to make sure it sounds right. Post-processing is like a final check. It makes sure the output sentence has the right punctuation and capitalization. It's like cleaning up the final draft of your story.
Decoder layer. The decoder layer. Unlocking the meaning and creating words. Imagine you're reading a story. You read the first few sentences and start to understand what's happening. The decoder layer is like your brain, taking all those words you've read and trying to figure out what comes next. What does the decoder layer do? The decoder layer is part of a language model, which is a type of artificial intelligence that learns to understand and generate human language. It takes the information from the embedding layer, which has turned words into numerical representations, and uses it to create new words or sentences. Think of the decoder layer as a puzzle solver. It has a memory of the words it has seen before, and it uses that memory to predict what words should come next. Example, let's say the sentence starts with, "The quick brown fox." The decoder layer has seen the quick, brown, and fox before. Based on its knowledge, it might predict that the next word is jumps, because that's a common word that follows those words. How does it predict the next word? The decoder layer uses complex mathematical formulas to calculate the probability of different words appearing next. It considers the context of the previous words and its own knowledge of language patterns. It's like a really smart guesser. Output. The decoder layer outputs a sequence of tokens, words, that represent the generated text. This sequence is then passed to the output tokenizer, which converts it back into human-readable text. In simple terms, the decoder layer is the part of the language model that creates new text based on what it has learned. It uses the information from the embedding layer to predict the next word in a sentence. It's like a smart guesser that uses its knowledge of language to create new and meaningful text.
Purpose. The purpose of each component in a model input and output chain. Think of these components as the different steps a machine takes to understand and respond to your words. 1. Input tokenizer. Imagine you are telling a story to a friend who doesn't speak your language. The input tokenizer acts as a translator. It breaks down your words into tiny pieces that the machine can understand. Example, instead of saying, "The quick brown fox jumps over the lazy dog," it might say, "The quick brown fox jumps over the lazy dog." Though, embedding layer, this is like giving each word a special code. The embedding layer takes those tiny pieces and assigns them to a specific location in a big, imaginary space. Words with similar meanings end up close together, and words with different meanings are farther apart. Example, the words quick and fast might be very close together because they have similar meanings, while quick and dog would be farther apart. Teen. Decoder layer. The decoder layer is the machine's brain. It uses all the information from the previous steps to figure out what you are trying to say and how to respond. Example, if you say, "The quick brown fox jumps," the decoder layer uses the information from the embedding layer to guess what word comes next. It might predict, over. Char. Output tokenizer. Just like the input tokenizer, the output tokenizer is a translator. It takes the machine's response, which is in those tiny pieces, and puts it back together into words that we can understand. Example, the machine might respond with the tiny pieces for, "over the lazy dog." The output tokenizer puts them back together to form the sentence, "over the lazy dog." 5. Post-processing. This is the final step where the machine makes sure everything sounds right. It might check for grammar errors, add punctuation, or make sure the sentence starts with a capital letter. Example, the machine might change, "over the lazy dog," to, "over the lazy dog."
Output tokenizer. Imagine you are building a machine that can understand and create human language. It's like a translator, but instead of just converting between languages, it learns to understand the meaning and structure of sentences. The output tokenizer is like the final step in this process. It's the part that takes the machine's output, which is a series of numbers representing words, and turns it back into a sentence that humans can read. Think of it this way. The machine learned to understand the sentence, "The quick brown fox jumps over the lazy dog," by breaking it down into individual words, tokens, the quick brown fox, etc. When the machine wants to create a new sentence, it uses those same tokens, but instead of having the original words, it has numbers representing them. For example, the might be represented by the number 1, quick, by 2, brown, by 3, and so on. The output tokenizer is like a decoder that looks at those numbers and says, okay, 1 is the, 2 is quick, 3 is brown, and so on. It puts those words back together to create a new sentence that humans can read. So, in short, the output tokenizer is the part that translates the machine's output, which is a sequence of numbers, into a human-readable sentence. It's like the final step in the translation process, ensuring that the machine's output is understandable to humans.
Purpose. The purpose of each component in a model input and output chain. Think of a model like a translator, trying to understand and communicate in your language. But it can only speak in numbers, not words. So, we need tools to help it bridge that gap. Input tokenizer. Imagine this like a code breaker. It takes your words and breaks them down into smaller pieces called tokens. This makes the information easier for the model to understand. For example, instead of the quick brown fox, it becomes the quick brown fox. Embedding layer. This is like a dictionary, but with numbers. It takes the tokens and gives them a meaning based on other words in the language. So, the words quick and fast might get similar numbers because they mean the same thing. Decoder layer. This is where the model actually thinks. It uses the information from the embeddings and the learned patterns to guess what should come next. Think of it like filling in the blanks in a story. Given the words, the quick brown, it might guess the next word is fox. Output tokenizer. This is like a reverse code breaker. The model has produced a string of numbers, and the output tokenizer translates it back into words for us to understand. Post-processing. Imagine someone writing a letter but forgetting to put periods and commas. Post-processing acts like a proofreader, checking the text and making sure everything is correct and easy to read.
Post-processing, the finishing touches for AI text. Imagine you've built a house, but it needs some final touches to be perfect. Painting the walls, adding furniture, and maybe even a beautiful garden. These are the final steps that make a house a home. Post-processing in AI text is like those finishing touches. What does post-processing do? After an AI model generates text, it often needs a little extra help to sound natural and correct. That's where post-processing comes in. It's like a final editor, making sure the text is polished and ready for humans to read. Here's how it works: punctuation and capitalization. The AI model might sometimes forget to add commas, periods, or question marks. Post-processing steps can add these in the right places and ensure the first letter of sentences is capitalized. Grammar correction. Just like humans sometimes make grammatical mistakes, AI models can too. Post-processing can fix things like wrong verb tenses or incorrect word order. Repetition reduction. Sometimes an AI model will repeat the same words or phrases, making the text sound boring. Post-processing helps identify and remove these repetitions, making the text more engaging. Stylistic adjustments. Maybe the text sounds too formal or too casual for the intended audience. Post-processing can adjust the writing style to make it more appropriate. Here's an example. Imagine the AI model generates this sentence: the dog runs quick in the park. Post-processing might fix it to: the dog runs quickly in the park. It added a capital letter at the start, changed quick to quickly, and put in a period at the end, making it sound more natural. In a nutshell, post-processing takes the rough draft of text generated by an AI model and makes it polished and ready for the real world. It's an important step in ensuring AI text is clear, correct, and engaging.
Purpose. The purpose of each component in a model's input and output chain. Imagine you are talking to a computer. It doesn't understand your language the way you do. It needs to be translated into something it can process. This is where the different components of a model's input and output chain come in. Each part has a specific purpose to make sure the computer can understand your instructions and give you the right answer. Input tokenizer. Purpose: to break down your words into smaller pieces the computer can understand. Example: Think of a sentence like, the quick brown fox jumps over the lazy dog. The input tokenizer would split this into individual words. The quick brown fox jumps over the lazy dog. Though, embedding layer, purpose, to give each word a meaning based on its relationship to other words. Example, the words quick and fast have similar meanings. The embedding layer would represent these words as similar points in a multi-dimensional space. This allows the model to understand that they mean almost the same thing. Decoder layer, purpose, to use the information from the embedding layer to predict the next word in a sentence or create a new sentence based on the input. Example, if the model has learned that the quick brown fox often comes before jumps, it can use this information to predict the next word when it sees the quick brown fox. Output tokenizer, purpose, to take the computer's output, which is in a code it understands, and translate it back into human-readable language. Example, imagine the computer has produced a series of codes like 123, 456, 789. The output tokenizer will convert these codes back into words like the quick brown. Post-processing, purpose, to make sure the computer's output is grammatically correct and readable. Example, the computer might add punctuation marks, fix capitalization errors, or change the structure of the sentence to make it sound more natural.
Example, let's break down each component's example to help understand how they work. Input tokenizer, example, imagine a sentence, the quick brown fox jumps over the lazy dog. Explanation, the input tokenizer would split this sentence into individual words, the quick brown fox jumps over the lazy dog. Embedding layer, example, imagine the words quick and fast are similar in meaning. The embedding layer would represent them as points close together in a multi-dimensional space. Words with different meanings would be further apart. Explanation, think of it like a map where similar words are near each other and different words are far away. This lets the model understand word relationships. Decoder layer, example, imagine you have the beginning of a sentence, the quick brown fox. The decoder layer tries to predict the next word based on the previous words. It might predict jumps because it understands the context of the sentence. Explanation, it's like a guesser. The decoder looks at the words it already knows and tries to figure out what comes next, using the patterns it has learned. Output tokenizer, example, imagine the decoder outputs a sequence of tokens, the quick brown fox jumps over the lazy dog. Explanation, the output tokenizer puts these individual tokens back together to form a complete sentence, the quick brown fox jumps over the lazy dog. Post-processing, example, imagine the generated text has a missing period at the end, the quick brown fox jumps over the lazy dog. Explanation, post-processing would add the period, making the sentence grammatically correct. The quick brown fox jumps over the lazy dog. Remember, these components work together to enable models to understand and generate language.